Hello everyone, my name is Pedram and I'm a professor in data analytics. Welcome to another episode of Deep Learning. Alright, let's get to part 2 of Module 5, Deep Computer Vision. In part 1, we talked about deep computer vision basics. We investigated what do we mean by human vision versus computer vision, and basically how and what actually computers see. Then we investigated the idea of why fully connected networks are not efficient when it comes to computer vision and why we should go beyond them. We talked about the basics of CNN, convolutional neural networks, and I showed you that how at a very high level CNN operates using something called filters or kernel. And we also talked about the parameters of a filter, which is size, stride, and padding. Now in this part 2, let's talk about the details of a CNN. All right, let's start by recapping the concepts of what is a convolutional layer. So as you know from the previous part, a convolutional layer consists of a bunch of filters that are convolved with input data to produce a set of feature map, right? So this is your input data. There you go. This is your input data. Then we have a convolutional layer. And in this convolutional layer, for example, I have 1, 2, 3, 4 filters. And each of these filters are responsible to extract a specific feature from the input data, right? So those features can be, for example, one feature can be used for edge detection, another can be used for corner detection or texture or color or things like that, okay? Then these filters, remember, they are learned. They are the weights of the model, right? They are learned during the training process. This allows the CNN to automatically learn relevant features from the input data. So this is important because this is the whole point of doing CNN, to extract these features automatically from the data. Then now the question is, why convolution? Why this operation works, or why is it a better alternative to fully connected layers? There are two main reasons. The first one is parameter sharing. Remember these filters, for example, the first filter, imagine this is the edge detector. They are useful, if a filter is useful in one part of the image, it is probably useful in another part of the image as well. So this means that if I apply a same filter like edge detector and I slide it over to the entire picture, then I just need to use the same parameters. So let's say it's a 3x3 matrix. We are going to use the same parameters and apply it to different patches of pixels, and we don't need to change those parameters, right? And basically, I'm going to have, let's say, 9 weights to be figured out at this iteration, right? So, and depending on how many of these filters we're going to use, we can multiply it to different number of filters. So, for example, this is a colorful picture. So we have 3 channels, right? So this is input data with 3 channels. Let's say it's a 28 by 28 picture, just for the sake of argument. So we have a 28 by 28 picture, multiply 3, right? Then we're going to say that let's go ahead and apply this 3 by 3 filter to the entire 3 channels. And how many of those filters you want to use? Let's say 10. So this is the number of parameters that in this convolutional layer we are going to learn. So this is the idea of parameter sharing. Okay, so we're going to apply the same parameters through the entire input image. Okay, so let's say, for example, here the answer is 270. So this convolutional layer is going to have 270. Let me see if I can write 200. Well, sorry, it's not working here. 270 parameters, right? So that's the first reason that why we should use convolution. The second one that we already talked about is a sparsity of connections, right? So what do I mean by that is that at each layer, so at each convolutional layer, the output value depends only on a small number of inputs, right? So for example, here the output only depends, let's say here, the output only depends on a small patch of the pixel, right? And this is very important because we talked about it. If you want to flatten this 28 by 28 by 3 image and then flatten it in a vertical manner and then feed it into the network, then the number of parameters is going to be a lot. So we don't need to have that global connection. We just need to have this local connections for extracting features locally. Okay, now let's put a bunch of these convolutional layers together. Let's stack a bunch of them with the pooling layers together and make a CNN, a convolutional neural network. Here is a more complex example where we're stacking multiple convolutional layers. remember, just like what we had in a simple, let's say fully connected neural networks, that at each layer we could have multiple neurons, here at each convolutional layer we can have multiple filters. So the idea is pretty much the same, but instead of neurons we have a filter. This means that at each layer we have a volume of images, right? So remember, multiple filters apply to the same input image and then stack together. So it's a volume of image, right? So look at this architecture for a second. So for example, let me use a right pen. So here is our input image. It's a 39 by 39 by 3, so it's a colorful image, so it has 3 channels. And then we are going to pass it to our first convolutional layer. Then the output of this one is going to be passed to the second convolutional layer, to the third convolutional layer, and then finally it's going to be flattened out and then passed to the output layer. So imagine the output layer here is a simple logistic softmax. Let's say we are classifying if it is a cat or dog. No, 2-class classification, we're going to use softmax activation function, right? Now, to review some of these parameters of the filters that we covered in part 1, let's do some of these calculations. So imagine the input size is 39 by 39 by 3. How do we get this output size? So where is this coming from? So remember, we had a formula that the shape in the size in the output is going to be equal to the size in the dimension width and height in the previous layer, and then we subtracted, we added back the padding, we subtracted the filter size or kernel size, we divided it by stride, and then we added number 1, and we said that let's go ahead and calculate the floor. Okay, so let's look at some numbers. So here is, let's use red. So imagine for this one we're going to get 39 plus the padding is 0, so plus 0 minus filter size is 3 divided by stride size is 1 plus 1. If you do the math and calculate the floor, it's going to be 36 plus 1, 37. So this is the 37, where the 37 is coming from. Where's number 10 is coming from? Number 10 is the number of filters that we use in this layer, right? So it means that we are stacking 10 of these filters. Okay, let's look at another example, make sure that you're following. So here, let's look at layer number 2. Where's this coming from? So here, basically, this is the easy number. We are having 20 filters. Usually in a neural network, in the CNN, we start with fewer filters, and then we increase the number of filters, and then we decrease it back, right? So let's say this one, this 17, is coming from, what was the input from the previous layer? 37 plus padding 0 again, minus, this is a kernel size, it's a 5 by 5 thing, matrix, minus 5, divided by stride, which is 2, plus number 1. So what do we get? We get 32 divided by 2, 16, plus 1, 17. So this is where the 17 is coming from. So hopefully now you have your confidence and in terms of calculating the input dimension and output dimension for each of these convolutional layers. And once we are doing the Python part, so it should be easy to recall where these number of dimensions are coming from. Okay, now let's look into the parameters in each of these convolutional layers, right? So this is going to be an important part because, again, once you're doing the Python part, you're wondering where's the number of parameters coming from, right? So let's take a deeper look into that. So imagine we have a 6 by 6 image, and this is a color image, so we are going to have 6 by 6 by 3, right? And we are going to apply the 2 filters. And those filters have the same properties, the parameters. So for example, the filter size is equal to 4, stride is equal to 1, and there's no padding. Okay, if you use valid padding. So if you do that, if you apply this filter to the input image, so what is the size of the output or the feature map? It's going to be 6 minus 0, plus 0 minus the filter size 4 divided by stride 1 plus 1, we get 3. So this is where the 3 by 3 is coming from. Okay, now let's look into the parameters, right? So remember, each of these, this is a 4 by 4 matrix, right? Each of these weights are going to be learned during the training, right? So I have 4 by 4, and you're using it 3. This is RGB. No, the number of channels in the input layer is 3. So I have to do 4 by 4. And then I have 3 channels, or the number of filters in the previous layer is 3. And then how many of these filters do I have? I have 2 of these filters, 1 and 2. So far, this is the number of parameters that we have, right? 4 by 4, 16 by 3, 48 by 2, 96. So far, there's 96 up to here. There's 96 parameters in the networks in layer 1, in convolutional layer 1, that needs to be trained, needs to be learned during the training process, right? And then at this step, we're going to add an activation function simply because to take care of the nonlinearity in the real world image data, right? So we talked about it in module 4 that why we have to apply activation function in neural networks in general. The same reasoning is true for the computer vision as well. So let's say we use the activation function relu, and then we're going to add the bias terms for each filter. So if I have two filters, we're going to add two bias terms for those filters, so the total number of parameters to be estimated in this convolutional layer is 98. So this is where the numbers are coming from when you're doing things in Python. You know, in the very last column, when you look at the model summary, there's a number of parameters for each convolutional layer, and if you're curious where they're coming from, here's how it's calculated. One last thing I wanted to emphasize is how these activation functions work, right? So for example, relu is an activation function that is going to give you 0 if the value is less than 0, and it's going to give you identical values as if the outputs are greater than 0, right? So this is our relu activation function. We're going to apply this relu to basically the feature map. No, this is your feature map. At the end of the day, feature map is nothing but a matrix or something like that. These are some numbers. Some of those numbers are positive, some of those numbers are negative, right? So imagine in this feature map, the black things are negative numbers in the pixel grid, and the white ones are positive values. So if I apply the relu to this feature map, so the negatives are going to be gone. It's going to be suppressed, and then the white ones are going to be the same thing, are going to just transfer identically, right? So this means that after applying the relu activation function, we go from the left-hand side feature map, let me use another color, to the right-hand side feature map, which is now have been incorporated nonlinearity into that. So basically here, the relu gets rid of inverse detection of that feature that you had in mind. So again, getting rid of the inverse detection means that the negative ones is going to suppress it to 0. So as I said before, we add nonlinearity because the image word is absolutely nonlinear. So that's it. This is the input of our convolutional layer. This is the output of our convolutional layer. Now we can stack a bunch of these things together and call it CNN. Okay, we're done with the convolutional layer. Now let's talk about the next one, which is a pooling layer, right? So pooling layer is usually not always, used to reduce the size of the feature map. And we do that for two reasons. First, to speed up the calculations, because now we have fewer multiplications to be done. And secondly, to get more robust feature, meaning that we want to get features that are less sensitive to small changes in the input image, right? And also note that pooling reduces the size and makes the model scalable, while at the same time it is still preserving spatial structure. So for example, if this is your input layer, whatever it is, and usually we do pooling right after a convolution, so this input layer is a feature map coming out of a convolutional layer, right? Then let's say it's a 4x4 thing, 4x4 matrix. And then, as you can see in this convolutional layer, there's a spatial, it preserved the spatial structure. After max pooling, whatever this operation is, after max pooling, still we are keeping the same, we are preserving spatial structure, right? We are not flattening things in a vertical manner or something like that, right? So that's important. There are two main types of pooling. One is max pooling and the other one is average pooling. In the max pooling, as the name suggests, we are going to look at depending on the pool size. So for example, if it is a 2x2 thing, we are going to look at 2x2 matrix from the input image, which can be a feature map, and then take the maximum value, right? So here the maximum value is 9, so we're going to use 9. Then in this orange or yellow square, the maximum value is 5, we're going to use 5. Here the maximum value is 6, we're going to use 6, and here the maximum value is 8, we're going to use 8, right? So this is how we go from a 4x4 feature map to a 2 by 2. Let's still call it a feature map, but it's after pooling layer has been applied to that, right? So this is how max pooling is doing the job. And for average, as you can guess, you're simply taking the average of these numbers. So the average of those numbers is 6, the average of these numbers is 3.3, and etc. Okay, so that's max pooling and average pooling. And just remember, guys, every time that you're downsampling, we are pulling like this in order to downsample the data or to input image, our filter is going to attend to a larger space in the input image. So this is really important. So what does it mean? It means that, for example, you start from a very high resolutional image, like, I don't know, let me make some numbers, 256 by 256, right? Now, if I apply a 3 by 3 filter, this means that each filter is going to focus on the local of 3 by 3, right? Of course, we're going to stride these filters over and etc., right? And then if I apply, so imagine there's a convolutional layer as an output, let's say it's 252 by 252, right? And now if I do max pooling, and let's use pooling to literally half the size, then I would have 128 by 128. So this new feature map is 128 by 128. Now, I'm not going to change the size of the filter. The size of the filter is still 3, so it's going to attend to a bigger region. And imagine we have a bunch of these convolutional pooling, convolutional pooling, convolutional pooling operations, and I don't know, maybe at the end of the day, we get to a feature map with a 5 by 5 only, 5 by 5. And dimension, right? So, and we can have a bunch of these ones. We can have, I don't know, 250 of these filters stacked together. But the point is that the size of the dimension of this feature map here is 5 by 5. Now, if I apply a 3 by 3 filter, we are attending to almost the entire image. So as you can see, we are doing this process in a hierarchical manner. In the first layers, we are learning low-level features, and in the last layer, we are learning high-level features. And this is an important point that you should keep in mind, that what is pooling, why is it doing, and what happens behind the scene when you apply those kind of pooling layers, right? Basically, your filter is going to attend to more chunks, or more patches of the pixels in the input image. So what are the properties of the pooling layer? So there are some parameters, hyperparameters. So the hyperparameters of pooling layer are just like the filter. We have size, stride, and type. And then remember, there's no parameters to be learned, so we are going to specify these things before training the model, right? And then unlike convolutional operations, just like the one that we just saw, pooling does not change the number of channels, right? So depending on what kind of convolutional operation we use, we may end up with different number of channels at the end of the day in the output, right? So, but the one that we covered so far is called standard convolutional layers, basically, or volume-based convolutional layer. And the way that it's done is that if I apply a filter, let's say this is a filter, and I apply to, I don't know, all these 3 channels, then the output was something like this, right? It didn't have a depth. However, if I'm doing pooling, so pooling, if I have 3 channels here, or again, depending if you're in the middle of the network, we don't call it channel anymore. These are simply the number of filters. So if I have 3 filters or 3 channels here, then the output is also going to have 3 channels, because we are applying this max pooling or average pooling to every channel separately. Okay, so I hope that this difference between pooling layer and convolutional layer is clear now. Okay, now we know what is convolutional layer, we know what is pooling layer. Let's put it together and construct our first basic CNN. So here's the input layer. Imagine this is a colorful picture with 3 channels, so that's why you see 3 channels here. And then we can divide this entire network into 2 parts. The first part is actually what we call feature learning part, which is done automatically. And the second one is basically your classification. Imagine these are pictures of a bunch of cars, and at the end of the day, you want to say that if it is a, I don't know, if it is a car, if it is a truck, van, bicycle, and etc. Imagine you have 10 different classes, right? Okay, so what do we do in the feature learning section? In the feature learning part of the network, the whole point is that take the input image, whatever it is, and make it to a lower dimensional high level features, right? So this is your lower dimensional high level features, right? So the whole point of doing this convolutional pooling layer is to extract those high level features, and then we can pass those high level features to the classification part. We're going to flatten them first. So here's the flattening part, and then we're going to add, I don't know, a bunch of other fully connected layers. We can add one or two. We can add some regularization like dropout if you wish. And then finally, we're going to pass it to the output layer, which is, in this example, is a simple softmax because we have 10 different classes, right? Now, inside this feature learning part, let's look into what we have. We have convolutional plus ReLU, and then we're going to do pooling, convnet plus ReLU plus pooling, and etc. So there are a couple of things I want you to pay attention. Look at that. As we go through the networks from left to right, the dimension, the width and height are shrinking, right? So the width and height are shrinking. So it means that, for example, here, maybe you start with 256 by 256 height and width of each image, and then you end up with, I don't know, maybe 5 by 5. So this is what we get in VGG16, you know, at the very last layer. So let's say this is 5 by 5. And so that's one thing that happens. And as you can see, you know, once we're doing the max pooling or average pooling thing, we go from, let's say, a bigger convolution to a smaller dimension feature map, right? And this is basically the point of why we're doing pooling, and because we want to reduce that dimension. And imagine, look at that, after pooling, we are doing another convolution, and we're doing it in such a way that the shape is not changing, right? So for example, we can use same padding, or we can just say stride is equal to 1 with same padding. So whatever the dimension is here, it's going to be exactly the same thing. In order to reduce the dimension, we're going to add another pooling layer, and then we can do this process on and on, right? So, and the number of filters that we use usually increase in the network. So for example, here, I don't know, we start with, let me use another color. Let's say we start with 32 channel, and then we go to, let's say, filters. We go to 64 filters. This is the depth, right? This is the depth of the number of filters that you're stacking on top of each other. And we can go 128 and etc. Okay, so at the end of the day, we may end up with something like 5 by 5 by 128. And then we're going to flatten this thing and then do the rest. Okay, now let's do this let's see how we can do this thing, because it seems complicated and daunting, but application of this using, you know, platforms like TensorFlow is just piece of cake. It's really easy. So let's look into that one. So imagine we want to write a code. We want to do our first CNN builder. So I'm going to make a function here. It's called CNN builder, and let me use blue color. And imagine we want to stack a bunch of these layers on top of each other, right? So how do we do that? So we're going to say, so this is the TensorFlow version of that, but the PyTorch version is not much different. So the idea is that we're just stacking layers on top of each other. Okay. So this is our input layer. Let me see, what color should I use? Maybe orange. Yeah, this is our input layer, right? So the input layer, imagine this is a 28 by 28. And imagine, for the sake of argument, this is a grayscale image. So there's only one channel, right? So 28 by 28 by 1. I can go ahead and call it input layer, right? In the next one, I'm going to stack my first convolutional layer. So this is conv2d. This is just the term that we use in TensorFlow. It's called conv2d. And as you can see, we're going to apply 32 filters. The filter size is 3 by 3. We're going to do stride 1, 1. And the stride by default is 1. You know, if you don't specify it, it's going to be equal to 1. And we say that the padding is valid. So it means that basically no padding. And we can use activation function, and that's it. So remember, this layer is built on top of the input layer. Then on top of that, we're going to add another layer. So this is our max pooling layer, right? So convolutional max pooling. For the max pooling, we're going to use pool size 2. So remember, that was a 2 by 2 thing. And then that's it. That's all we want to specify here. So we're going to stack a bunch of these things: conv2d max pooling, conv2d max pooling, conv2d max pooling. And then at the end of the day, we're going to flatten things. So we're here now. We're going to flatten things. And then after that flattening, we can add a dense layer. We can have multiple of these dense layers. And after each dense layer, you can add a dropout if you wish, if you want to regularize the network more. And then finally, you have your output dense layer, which is this one. And for this example, we're using 10 units because there are 10 different classes. Activation function is softmax, and that's it. And after that, we are going to go ahead and build the model. The inputs are these things, and the outputs are these things. And when we want to compile the model, simply we say use this specific optimizer. Our loss function is sparse categorical cross entropy, and metric is accuracy. Okay, so here the loss function. So this is another example. This is for MNIST data, but we are looking at this image. So for the image classification, the loss function, we can simply use categorical cross entropy. All right, now let's look into a cool visualization of the CNN. Now, this is actually a paper written by Adam Harley. So here's the link if you want to play around with this visualization on your own. And basically the title of the paper was Interactive Node Link Visualization of CNNs. So let's look into that. All right, here we are in Adam Harley's website. Let's look into this cool visualization for the CNNs. So here's a paper if you're interested to read that one, but I'm going to scroll down and navigate to, actually, let's look into fully connected networks versus CNNs. So the first one, let's look at a 3D version of the fully connected networks. We are going to work with a 28 by 28 image, and so these are handwritten image recognition, right? So, and then we are going to do two hidden layers. The first one has 300 nodes and the second one has 100 nodes. So let's look into this one first. All right, I'm going to pull up my calculator. Let's see. Let's pull it up, calc, and let's do some simple calculations together. Okay, so I'm going to go ahead and write some number here. Let's do number 3. Okay. So here is how the network is going to look like. So this is the input image, and surprisingly, the output, well, the algorithm didn't realize that this is number 3. So the first guess was 2, the second guess is 1. So neither of them is even close to what we have. So let's see how it's doing the thing, right? So this is your input layer. We said that if I want to use fully connected layers, we have to flatten this thing, right? It's a 28 by 28, right? So we get our 28 by 28, so we have 784. So if you vectorize this thing, right, and then we need to connect these things to every single node in the next layer, right? So if you look at that in the first layer, how many nodes do we have? We said I think 300, right? The last one, if you click on it, yeah, 299, 300, right? So we have 300 nodes. It means that every single of these nodes are fully connected to 784 of these pixels, which is vectorized, right? So as you can see right away in the very first layer, there are so many parameters to be learned. Remember, each of these blue lines has a weight associated to that, right? So this means that if we have to do something like this, we have to do 28 by 28. So this is flattened. And then we need to multiply it by 300 because we have 300 nodes. And we need to add 300 bias terms. So right at the very first layer, we have 235,500 parameters to learn. And then, of course, we have to add more parameters in the second layer. So what do we have? So in the second layer, we have 100 units. So this means that we need, and so 300 here. So it means that, let's pull up the calculator again. It means that 300 multiply that 100 plus we are adding 100 bias terms, so 30,000 here. So 30,000 here, 250 something thousand there. So already this simple network with only 2 hidden layers, not many number of nodes as well, it has 200,000 plus parameters. So this is a lot, right? So this is a lot, and of course, and as you can see, it's not doing a good job, at least in this version that he put together, right? It doesn't have a good output, and it's not able to guess what was the number. So let's try another one. Let's do number 2. Yeah, it's able to capture number 2. This is great. Let's do another one. Maybe 4 is one of those numbers that's difficult. So it's getting it 9. If I write it like this or this, yeah, if I write it like this, it's going to figure it out. It's number 4. And this is our output layer, right? So we are doing some, the loss function is a sparse categorical cross entropy. And we are doing some softmax, and the output of the softmax, these are some probabilities, right? And it seems that this one, number 4, has the highest probability. All right, So that was the fully connected layer if you want to do some handwritten digits, let's say, classification, right? Let's look into the convolutional version, right? The CNN version. So let's click on it. And now we are going to have, so in this example, we can switch them on and off, by the way. But let's say we have two convolutional layers, two fully connected layers, and two pooling layers, right? So let's go ahead and write down number 3 that the previous one was not able to capture. Okay, this one got it, right? So the CNN perfectly captured our number 3. The first guess is 3, the second one is 1. So we only care about the first guess, right? So let's see what is inside this CNN. Remember, this is your input, right? It's a 28 by 28, I assume. And then you have a conv layer number 1, pooling layer, conv layer number 2, pooling layer, and then the fully connected layer number 1, fully connected layer number 2, and finally apple layer. So there are a couple of things I want to highlight. So the first thing is that as we go deeper in the network, the size of this thing is going to decrease. So the dimension of the layer is going to decrease, the width and height. This means that we can use the same filters, the same size filters at each convolutional layers, and those filters are now deeper in the network. They're attending to a bigger chunk, bigger patch of the input. So this is one thing. And then as we go deeper in the network, we have the luxury to work with many more filters, right? Because now the input shape is reduced. So let me actually walk you through this one. Input level, and then I'm going to use 1, 2, 3, 4, 5, 6. This is 6 filters applied to the first input layer. And as you can see, each filter is trying to capture some specific pattern, right? So we don't know what it is. These are automatically detected, but whatever it is, it has been learned by the network, right? And the cool thing is that remember, if you want to compare this one with this one, here the fully connected layer is attending to all the pixels, right? This is a kind of global fit, and it's not efficient necessarily. But this one, look at this, for example. The conv layer number 1, it's attending to only patches of data, right? So if the filter is 5 by 5, which I think it is 5 by 5, so this is filter number 4. Yeah, I think the filter size is 5 by 5, and it's attending to a 5 by 5 area, the patches of pixels. So each filter is attending to 5 by 5 thing. Okay, and then we are going to reduce the size by doing max pooling. So this is our downsampling layer, let's say max pooling. And then we're going to apply another, look at that, if I go deeper in the network, now we can afford to have more filters because the size has been reduced, right? So let's say here we have 16 filters, and now the filter size is the same. The filter size is 5, and I hope you realize that we are now attending to bigger patches of the data compared to here, right? And then again, we're downsampling it. And after this, we have 16 filters which are downsampled. This is our feature map that are reduced in terms of size. Now we are ready to flatten these things. Whatever the size of this is, we are going to multiply it by 16 and then flatten it as a vector. And so this is our fully connected layer, and then this is our second fully connected layer, and finally this is our apple layer, the same apple layer we use. Let's try out a bunch of other numbers. So maybe number 4. I'm curious to see. Oh, great, right? So this is going to capture number 4 as well. And then we can have number 4 like this. Great, so it's doing a great job. Our simple neural network is doing an excellent job. All right, I hope you enjoyed this one. And now let's go back to the lecture. Okay, as far as the CNN architecture, this is all we needed so far, right? And for the rest of these slides, I will talk about different, some other convolutional operations that we're going to use them later in the course. So for example, for semantic segmentation, for object detection, we may end up using different convolutional operations, and we will not use this standard volume-based convolutional operation. So let's take a look at these ones and then wrap up the section. Okay, starting with convolutional operation on volume. So this is also called standard convolution, and this is what basically we use in the TensorFlow. We call it conv2D, right? So let's see, what is the idea. The idea is that a filter should have a matching number of channels if the input has more than one channel, right? So for example, if you have a color picture, there are 3 channels RGB, right? And then that means that you need to have your filter needs to have the matching number of channels. Your filter needs to have 3 channels in this example. So in order to calculate the output cell, so basically your feature map, we're going to apply this convolutional operation to each of these matching channels and then simply add them up, add up the results. So it means that, let's look at the numbers here. So here you have one 3x3 filter. There's only one filter here, but this is the first channel of the filter, if you wish. We're going to multiply it by this 3 numbers, 3x3 numbers, and then we're going to repeat this process for the other channels as well. Okay. Basically something like this. All right, so what does it mean? It means that, for example, if I have a 3x3 filter, then it means 3x3, and we only have one of these filters, okay? And then there are 3 channels to this filter, so it means that this is going to give me 27 parameters to be trained. So basically 27 of these numbers, okay? 9 of them and 3 times a stack on top of each other. So this is our 27 parameters. Okay, now remember we can use multiple of these filters and stack them together, right? So let me actually do some of these calculations. Again, if you're quite familiar and comfortable doing these things, you can skip this part, but I just want to make sure that we understand exactly what's happening. Okay, so we know where is this number 27 is coming from. Let's see where is this 4x4 is coming from. Remember the input is 6. So I'm going to say 6 plus no padding minus filter size, which is 3, divided by stride size, which is 1, plus 1. So if you do the math, you should get number 4. Okay, so that's where the 4x4 is coming from. Now let's stack a bunch of these filters. So let's use the same input image, 6 by 6 by 3. These are the number of channels. Each filter needs to have 3 channels. So how many parameters do we have? 3 by 3. These are the number of, so for example, at each channel of the filter, we have 3 channels, and now we have 2 filters, filter number 1, filter number 2. So I'm going to add it by 2, multiply it by 2, and of course I remember to do it in a previous one. We have to add the bias term as well. So there's one bias term for one bias for 1 filter here, and 2 biases for 2 filters here. So here we're going to get 3 by 3 by 3, 27, 54, 56 parameters here, and here we are going to get 28 parameters. All right, and this is our output. This is a feature map, right? So the feature map now has 2 channels. We can call it filter as well. So if you pass it to the next layer, then we have to be careful that whatever filter we apply, it's going to be 2 multiply 3 by 3 by number of filters that you're applying in the next layer. Let's say in the next layer we apply 5 filters, right? So the number of parameters are going to be 3 by 3, 9, by 2, 18, by 5, 90, plus, let's say, 5 bias terms, 95. All right, so this is how we calculate the number of parameters for a convolutional operation on volume. So this is a standard, also we call it standard convolution. All right, so let's look into the next one. All right, the next one is depthwise convolution. So this convolution is a type of conv operation that operates on each channel of an input volume independently. So in other words, the filter has the same depth as the input volume, and the convolution is applied separately to each channel. So let's look at this visualization. It's going to help a ton. So here we have a 12 by 12 by 3, so let's say RGB channels, and now we are going to use one filter. See, this is one filter. However, this filter has 3 channels, so the number of channels of the filter is the same as the number of channels of the input layer, right? So if you're in the middle of the network and your feature map has 10 layers or 10, let's say, features or filters or levels or depth, then your filter needs to have 10 depth, right? So this means that we are going to apply each of these channels of the filter to each of the channels of the input image. So we're going to do a conv operation, to pointwise multiplications, and then come up with an output. And the big difference between depthwise convolution versus the standard convolution is that, look at the output. So the output here is has 3 channels, right? However, in standard convolution, the output had only 1 channel. So this means that the output of a depthwise convolution is also a volume with the same number of channels as the input, right? So if I wanted to generate something like this, with a standard convolution, I needed to use 3 filters, but here I only use 1 filter. However, remember the number of parameters are the same, right? So for example, here I have a 5 by 5. Let's say we are going to use 1 filter and we have 5 by 5 and by 1, and we're going to apply this 3 times for 3 channels. So we're going to get 45, right? And if I use a standard convolution, I get the same 45 numbers for parameters. And of course, we're going to add the bias terms and etc. Okay, so that's one thing. The other thing you should remember is that, okay, why should we use depthwise convolution? So the idea of depthwise convolution is to take care of 2 things. One is the spatial dimension. For example, we apply 1 channel of a filter to this, and this is going to preserve the spatial relationship. And at the same time, we believe that there is something in the depth dimension, right? So we want to treat these layers, we want to treat these channels of the input image differently. We want to make sure that we're preserving those changes, those nuances within the depth of the input image. So if you want to do that, we're going to use depthwise convolution. Then the next one is actually pointwise convolution. Okay, so what is pointwise convolution? We also call it one-by-one convolution. It's actually a comp operation that the filter has the size of 1 by 1 by c, and c is the number of channels, right? So for example, here we have 8 by 8 by 3 input image, and now we're going to apply this 1 by 1 by 3 because our input image has 3 channels, right? And then this is going to help us to reduce the number of channels of the input. So the channels of the inputs go from 3 to 1. But we didn't touch the dimension. So the dimension used to be, width. By dimension, I mean width and height. So it used to be 8 by 8. Now it is still 8 by 8. Remember, in the depthwise or standard convolution, if the filter size was anything greater than 1, we use, let's say, no padding, we know that the output has a lower dimension. But here, if you look at the dimension, what do we get? 8 plus 0 minus 1 divided by 1 plus 1. So we get back to number 8 here. So as you can see, the dimension doesn't change, but the number of channels is going to be reduced to 1. So that's basically why we use pointwise convolution. It is used to reduce the number of channels in the output volume, in the input volume, or to combine multiple channels in the input volumes into a single channel in the output volume, right? So this is basically why we use pointwise. And also remember that this convolution can be thought of as a linear transformation of the input channels. So the whole point is that dealing with the channels, right? And you want to come up with a linear transformation of those channels. Let's say we have 5 different channels. We want to come up with a linear combination of those 5s and make it transform into 1 channel. This makes the one-by-one convolutional useful for learning channel-wise relationships in the input data, right? So we're not going to apply one-by-one convolets, in a vacuum. Of course, we have to combine it with with standard convolution, with depthwise convolution, and make sure that we're looking at spatial relationships as well as the depthwise relationships, like something like this. The next one is called depthwise separable convolution. So the idea is that we use depthwise convolution usually in conjunction with a pointwise convolution, right? And we are going to put this together, and we are building something called depthwise separable convolutional neural networks. So this kind of network architecture is usually more efficient and faster to train compared to traditional convolutional neural network because it has fewer parameters and of course fewer number of computations. So in the next slide, I'm going to show you an example that numerically what is the difference between number of calculations that we do using standard convolution versus using depthwise separable convolution. So because of that, this architecture is usually used in mobile-based application, when of course we have limited access to computation power. Also remember that this network is used in models that needs to learn spatial features from different channels separately. So remember, we want to keep track of spatial features, and at the same time, we want to treat different channels differently and to extract features based on different channels. So this kind of convolution we're going to use this later in the course when we're doing image segmentation or object detection. Okay, now let's look into that numerical example. So basically we want to see why depthwise separable convolutions are a lot more efficient and computationally lighter compared to standard convolutions, right? So imagine here's the goal. We have an input image of 12 by 12 by 3. So this is let's say there are 3 channels. We want to go from this input to this output. So this is, let's say, our feature map in the middle or at the very last layer of the network, right? So we want to go from 12 by 12 by 3 into 8 by 8 by 256. So the whole point is that we're going to reduce the dimension of the data from 12 by 12 to 8 by 8, but now the depth of the data is a lot more. You know, we can have 256 different filters to capture any kind of behavior, feature that the network can extract from the input image, right? So that's the goal. So let's use traditional convolutional operations. So what do we do? Imagine, so we're going to have one filter here. So this is our filter, and we are going to do 5 by 3, 5 by 5 by 3. Remember, there are 3 channels because we want to, this is a volume base, right? So we talked about this in the previous slides. And then I'm going to move around this box 8 by 8 times. So where is this 8 by 8 times coming from? Remember, this is number 12. So 12, if there's no padding, 0. If the filter size is 5 divided by stride 1 plus 1, I'm going to get number 8. So this means that if I basically move around this box 8 by 8 times, I'm going to, well, you get the idea. I'm going to cover this entire, with no padding, I'm going to cover this entire input image, right? So that's where the 8 by 8 is coming from. So, and then at the end of it, we're going to repeat this process 256 times because we want to have 256 filters. So what is the number of calculations? 256 of these things, 5 by 5 by 3, which is moving around 8 by 8. So the final output number of calculations is 256 by 5 by 5 by 3 by 8 by 8. So if you do the math, you're going to get 1,228,800 multiplication. Remember, this is multiplication, not the number of parameters. The number of parameters, of course, is going to be a lot less. Okay, so that's the standard convolutional operation. For the depthwise separable convolution operation, we are going to divide it into 2 parts. You know, let's say the first one, which is a depthwise, the second part, which is a pointwise operation. The depthwise operation, the number of multiplication is pretty much the same as what we have in the first part of the traditional convolutional operation. So why? Because let's say here we have one filter, but we're going to treat these channels differently. You know, we have 3 channels for this filter. And so basically we have 5 by 5 by 1, but we're going to apply these 3 channels to that. And then we're going to move around this thing again 8 by 8 times. Okay. So you get the idea. There's going to be 8 horizontally, 8 vertically to get to this kind of output, right? So basically the first part is the same. So we're going to, there are 3 5 by 5 by 1 kernels that are going to move around 8 by 8 times. So 5 by 5 by 1 multiply 3 by 8 by 8. So this is pretty much the same as this one. So there's no difference in that sense, right? So the big difference is in the second part. So here we have 3 channels. We know that we can use pointwise operation to reduce the number of channels to whatever we want, right? So for example, if I use 1 by 1 by 3, I'm going to reduce the number of channels from 3 to 1. Okay. So now that we have 1 channels, we're going to repeat this process 256 times. So the second step is, you know, we have 256 of these kernels 1 by 1 by 3 that are moving around 8 by 8 times. Again, why 8 by 8? Because the dimension, if you remember from previous slide, is not going to change. So if I move around this thing 8 by 8 times, then we're done, right? So we're gonna repeat this 256 times. So 1 by 1 by 3 by 8 multiply 256. If you do the math, you're gonna get 53,952. So the number of multiplications in depthwise separable convolution is a lot less compared to basically here standard convolutional operation. Don't worry about the details of the calculations. Of course, you're never gonna do that, you know, manually, or even you don't need to think about it. But just be aware, if at some point you're curious what's happening behind the scene, why the depthwise separable convolution is a lot faster, and it is designed to be used for, I don't know, for if your processing power is, for example, you want to apply a model in your mobile device, right? Just be aware. Just be aware that this is what's going on, but don't sweat over it. Don't worry about it. Don't fret. It's absolutely not necessary to understand these kind of things, but at the very high level, just know the difference between these kind of operations. So the last one that I want to cover is, basically transform convolution. All right, so the last thing I want to cover is called transposed convolution. So it is called transposed simply because it uses a transposed version of the convolution operation to achieve upsampling. So it is a type of conv layer that is used to upscale or upsample the feature map produced by a convolutional neural network, right? So the idea is that, let's say whatever the input is, this can be your feature map, right? Coming from previous conv layers. And let's say it's a 2x2 thing and you want to increase the size to a 3x3, right? Later in the course, we will see that why we are interested in doing things like this. So for example, when we're talking about autoencoders, this is the original image. Let's say it has, I don't know, 256 by 256 size. And we're going to encode it to a very high level features, but low dimension feature map. Let's say, I don't know, just dimension wise, right? I'm not talking about the depth. Let's say we bring it down to 5x5. And then we're going to decode it again to the original size of the image, 256, right? So we're going to apply a bunch of these transposed conv layers down the road to achieve this goal. And the operation is it's very straightforward. Let's look at this example. Imagine the input is 1, 2, 3, 1. We're going to apply this filter, filter of size 2x2. And the calculations is just, again, transpose of the convolutional operation. So it is color coded, so it should be easy to follow. So first of all, we're going to multiply these four numbers by this. So this is where we get the blue one. And then we're going to multiply those numbers by the red. So basically 2 by 2. So look at that. I'm multiplying these 2, 3, 3, 0 by number 2. So I get 4, 6, 6, 0. Then I'm going to multiply it by number 3. I will get 6990, and then finally I'm going to multiply it by number 1. I will get 2, 3, 3, and 0. And I'm going to stack them together. Simply we can go ahead and add them. Depending on what size of the output you want to get, we can basically put these things together in a way that we get to in this example 3x3 output, right? Then we're going to add them, right? So for example, this 2 plus 0 plus 0 plus 0 is 2. All right, that's pretty much everything you need to know for understanding the CNN architecture and basically what are different types of convolution operations. So in the next one, we will be talking about the concept of transfer learning and basically looking at some of the classical CNN architectures out there. All right, until the next one, take care.